Hello student to the foundation of classical electrodynamics course. So, under module 2 today we have lecture number 27. So, in today's lecture we are going to understand something about electrostatic potential. So, today we have class number 27. So, in the last class let me remind what we have in the last class. In the last class we had the Gauss's law. So, we know this, the divergence of E, where E is the electric field, is rho by epsilon 0. And if I want to find out the integral form, then it should be E dot ds closed integral should be something like q enclosed divided by epsilon 0. This is the differential form and this is the integral form of the Gauss's law. So, we did few calculation also to find out the electric field for certain distribution of the charge. So, today we will going to continue that and then we will try to understand what is electrostatic potential. So, we should do the problem related to uniformly charged sphere. Uniformly charged sphere. So, when the charge sphere is given and you can try to find out the field, there are two ways to find out the field, one is inside and another is outside. So, suppose this is a charge sphere with certain coordinate system and try to find out the electric field at any point outside. Suppose the radius of this field is r, this sphere is r, and try to find out the electric field at some point outside. So, the condition is r is greater than r. So, I simply use the Gauss's law that E dot ds is equal to q enclosed divided by epsilon 0. So, that means I should consider a bigger surface having the radius r like this. So, this is my Gaussian surface, and if I consider that Gaussian surface, then for closed surface integral it should be q enclosed divided by epsilon 0. So, eventually we have E and the total area is simply 4 pi r square, and that should be equivalent to total charge. Suppose the total charge is q, that is enclosed, divided by epsilon 0. So, simply my E should be q by 4 pi epsilon 0 r square. If I want to find out in the vectorial note, then this should be the electric field. So, that means it seems that the total charge is centered at the point this origin, and due to that charge I am getting the electric field at point r. When the r is greater than big R, that means it is outside the sphere. Well, a same problem can be done for, suppose I want to find out what is the field inside. So, this is the sphere we have with certain coordinate system, and the point is, and this radius is like before r. Now my point is not outside but inside, this is r. So the question is, what should be the value of E at this point under the condition r is now less than big R. Okay, so we will going to use the same process, like we will make a Gaussian surface here, and that surface is essentially a sphere as per the symmetry is given, and for that you have, now I have E dot ds is charge enclosed. You have to be careful enough because now the total charge enclosed is not q, that is the basic difference we are going to have here, divided by epsilon 0. So it should be E 4 pi r square, this is the area, and then the charge enclosed I can calculate, but in order to calculate that I need the charge density. Suppose the total charge q is uniformly distributed in this sphere. So total charge q, if it is uniformly distributed over this sphere, then we have this. The relationship between q and rho should be this. So rho is given. So in terms of rho I can have the value here. So what should be the charge enclosed then? The charge q enclosed should be this volume rho multiplied by the volume of this, which is this quantity. Okay. So my right hand side should be 1 divided by epsilon 0 and rho and 4 by 3 pi r cube. Now I can simplify this, it should be E is equal to these 4 and 4 seems to be cancelling out, pi and pi seems to be cancelling out, 1 r square is cancelling out, having r only. So eventually we have 1 by 3 epsilon 0 and then r multiplied by rho. Now if I want to write the entire electric field in terms of the q, that is total charge, I just simply replace rho in terms of big Q. So then it should be 1 divided by 3 epsilon 0, then r, and rho should be q divided by 4 by 3 pi and then big R cube. So it should be q r divided by 4 pi epsilon 0, 4 pi epsilon 0, and this 3 will cancel out, and then 4 pi and epsilon 0 should be there, and then r cube. So that is the value of the electric field, and if I want to find out in terms of, if I write in terms of vector, then that should be the field when r is less than r. So that means in the outside it varies as a function of 1 by r square, but in the inside it varies as a function of simply linearly varies as a function of r. So if I plot that quickly, that how electric field should vary. So electric field for the sphere as a function of the distance r, and then you can see that curve is something like that. It is linearly changing up to the point when r is equal to r, and after that is decaying like 1 by r form, and this side we are plotting r. Okay, so this is the way the electric field will going to change. This is a very standard problem. I believe most of the students have already done it. But if you want to calculate the uniform the field due to uniform charge sphere in a rigorous manner, it should be a very lengthy calculation. So, in order to reduce this calculation, one can use this Gauss's law, and using the Gauss's law, these things will be very, very simple. Now, we jump to the next very important part where we calculate. So, let me use the new page here. So, here we try to understand first what is the curl of the electric field. So, the curl of E. So, divergence of E, mind it, we already calculated. I just write here divergence of E, we figure out that it is simply rho divided by epsilon 0. The question is, what is this value? So, curl of E means what is this value? If I want to find out the curl, then what we supposed to get here, the right hand side. Okay, so in order to understand that, let us consider a coordinate system, standard coordinate system, say x, y, z, and a line element here like this, going from point A to point B. Okay. So, now the charge is one charge is placed here at the origin Q, and due to the placement of the charge here at the origin, it should produce some kind of electric field over the space, and I need to calculate. So, my goal here is to calculate the line integral here. Simply I want to calculate first A to B, the vector field E is given, and that I calculate over the line. So, eventually I calculate the line integral. Well, here these, because the electric field we know here due to the placement of the charge, the electric field that we will going to have in this space is simply the magnitude of the electric field, or in the vector, if I write in the vector form, it should be Q divided by 4 pi epsilon 0, and then r unit vector divided by r square. So, you can see that electric field is given as a function of r. That means it is in spherical coordinate system. The field, the vector field is given the spherical coordinate system. So, that because of that, my line element, whatever the line element I draw here, should be in the cylindrical coordinate system, and we know how to write the line element in cylindrical coordinate system. It is dr r unit vector plus r d theta theta unit vector plus r sin theta phi unit vector. So, this is the line element I have, because the vector field that is given in spherical polar coordinate, my line element should be also in that unit, also in that coordinate system. So, now we are in a position to calculate the integral. So, let us calculate, because I know explicitly the value of E and dl. So, my E dot dl should be Q by 4 pi epsilon 0, that quantity is constant, that will come outside, and then integral point A to B, and note it, E is along r unit vector, and dl is r unit vector associated with theta unit vector and phi unit vector. So, r dot theta and r dot phi will not going to contribute. So, the thing that we will have inside the integral is simply 1 by r square and dr, and that thing is simply q by 4 pi epsilon 0 minus of 1 by r point A to point B. Okay. So, that quantity if I write, so q by 4 pi epsilon 0, then 1 by r A minus 1 by r B. So, that is the value. So, what is R A? So, R A is, if I join these 2 point in spherical coordinate. So, this should be my R A and this should be my R B. So, now you can see that the total integral only depends on the final point, and that means if I want to calculate the total integral, closed line integral of this quantity, suppose I have a closed loop and I calculate this quantity over this closed loop, then R A and R B, these 2 points should be the same point, that means they coincide. So, that means this quantity in the right hand side should be 0. So, I should have simply 0 here, because this is a path independent integral, it just depends on the initial and final value. So, considering that, so considering this thing, I can write that if the integral is 0, then using the Stokes law I can have from here, I can have another important information, and that is this quantity is nothing but curl of E. Mind it, from the very beginning I wanted to calculate the curl of E, and over this surface integral this has to be 0. Okay. So, from this equation, this is true for any surface, this is true for any surface. That simply gives me a very important information, that curl of E is 0. So, the electric field should not have any kind of curl. This is a fundamental relation that we develop, and we will going to exploit this further to find out the concept of the potential. So, let us jot down what we get so far. So, we have divergence of E is rho by epsilon 0, and curl of E is 0. These 2 information we have in our hand. So, from that we will going to develop the concept of electric potential. So, let us write it here. So, next thing is electrostatic potential. So, we have this information, curl of E is equal to 0, that gives me, because I got it from the condition that if I calculate from some point A to B the line integral E dot dl, then the result what I get is path independent. This is path independent, depends only on the point A and B. It only depends on the initial and final point A and B, only the end points. So, I can, in that case, if this is the case, then I can define a scalar quantity. We can define a scalar quantity which should be a function of r as this. I just define this, that this is a scalar quantity, and these things means, since it is a path independent, so I can have phi b is minus phi a. If I calculate by defining this, I can simply have minus 0 to b e dot dl, and then plus a to b, because we have only minus sign here, sorry, 0 to a, then e dot dl, this quantity we have. So, then I can simply write it as phi b minus phi a as minus of 0 to b e dot dl minus a to 0 e dot dl, and that is essentially my minus of a to b e dot dl. Okay. So, that means I can have, after making this integration, I can have phi a minus phi b. So, I can write phi b minus phi a, because I am getting this as an result of the integration. I can write it at simply a to b and then a to b, then d phi, and we already know that d phi I can write in terms of the gradient operator, and it should be simply this. We did it in our earlier classes. So, that I replace here, and it should be a to b and then gradient of phi dot dl. I just write in terms of d phi, and that quantity is nothing but minus of a to b and then e dot dl. So, from these two equations, from here to here, I can simply write a to b, then e minus not e minus, e plus this quantity is identically 0, and this is true for any line segment, So, that means I can define E in terms of a quantity phi which we call the potential. This is called the electrostatic potential. So, I can define E, the electric field, in terms of a scalar field phi whose gradient and negative of that gives me the total electric field, and that is the electrostatic potential. Well, here if I want to find out ith component, it should be simply the scalar field divided by xi. Okay, this is the component form. Now, we will do another thing quickly, and that is concept of potential. From Helmholtz theorem, because if you remember, so if we remember the Helmholtz theorem, so the Helmholtz theorem was suggesting that if I know the divergence and curl of a vector field, like here I know this, the divergence and curl of the vector field is known, this is known, right. The question was, what should be the E in terms of these known parameters? Can I expand, can I write E in terms of these things uniquely? And the answer was yes, we can do that. So, in general, E can be written as this form according to the Helmholtz theorem, that I can write, I can decompose my total electric field into two parts. One is the gradient of a scalar field and another is the curl of a vector field, say V here. Okay. And the scalar field and vector field is defined by the curl and these things. So, what should be my phi here? What should be my phi here? My phi according to the these things 1 by 4 pi integration whatever the curl I am having, whatever the divergence I am having, so that divergence value. So, divergence of E and divided by r minus r prime and dv prime, that should be my phi. And what is my V according to the Helmholtz theorem? My V should be 1 divided by 4 pi and integration of whatever the curl I am having at r point and then r minus r prime and then dv prime with this. Now, you can see this quantity is 0. So, the vector potential for the electric field is 0, but the scalar potential is not equal to 0. What is the scalar potential phi? Phi according to the Helmholtz theorem is simply rho divided by epsilon 0, because this is known, and it should be r minus r prime dv prime. Mind it, this rho should be calculated at the point r prime. So, I can write in a more compact way, this is 1 divided by epsilon 0 integration rho calculated at r prime and r minus r prime dv prime. Note it, all this calculation or whatever the derivation we have, we did it from on the basis of Helmholtz theorem, because in Helmholtz theorem these things was already mentioned that if you have the information of the divergence and curl of a given vector field E, then the vector field E in general decomposed by these two, that it should be a minus of gradient of the scalar field and the curl of a vector field, where the scalar field and vector field can be defined in this way, where this inside the integral I have the information of this known thing, that the divergence and curl. For electric field we find that the curl of E, since it is 0, so there should be no vector potential. So, no vector potential for electric field. Okay, no vector potential for the electric field, but the scalar potential is there, and the scalar potential is simply this, and that is precisely today's task. So, we wanted to define the vector potential and the scalar potential for the electric field, and since curl of E is equal to 0, that gives me that there is no vector potential associated with the electric field, but we have the scalar potential for the vector field, which is called the electrostatic potential. For magnetic field we will going to see that the vector potential is non-zero, but there should not be any scalar potential. So, with that note I like to conclude today's class. In the next class maybe we will going to discuss about more about this potential thing, and if possible a few problems. So, thank you very much for your attention and see you in the next class.